So I'm going to talk about iterators, generators, and coroutines. And these are all related to concurrency, but they are not the same thing, and that's an important. It's typically you have them bundled together with the possibility of doing things in parallel, speeding things up. But they are two different things. So as you can see, you can have concurrency without talking about these kinds of streaming concepts, and you can have streaming without having concurrency too. So those are sort of orthogonal, but they usually, but clearly, it's a match made in heaven. So let me talk about iterators, and I'll talk first about iterators, and you'll see some part of the picture. Then I'll talk about generators, and you see a little bigger part of the picture. And then I'll talk about coroutines, and you see the whole picture, a little bit more kind of a very general picture of other ways of thinking about functions. Mainly that's what's going on. Actually, function implementations, other ways of thinking about function implementations, rather than the normal stack based implementations. So let me talk about iterators. Now I'll start with an example of what you all probably have seen iterators. You've used iterators. If you use Java or C# or one of the modern programming languages, when you're iterating through some sort of a collection, a list, or whatever, you very likely have used the iterators that the language provides. You may not know what they are and what exactly are they made of, but you've used them, so you've seen them from the outside. This lecture is to see them from the inside. What exactly are iterators? So first of all, let me just tell you what the problem is that iterators come to solve. Where do iterators come from? And basically, the problem that they're trying to solve are the problem of having to have accidentally large intermediary collections, lists or whatever. So here's an example. I'm going to run with this example. Suppose that we want to print out a stream of positive random numbers less than 1. So some number between 0 and 1, where the difference between every two numbers in the sequence is greater than 0.4. And then you stop when the number that you get is less than 0.1. So you roll a dice to keep throwing, these real numbers between 0 and 1. Make sure, if the difference between this one that you rolled and the previous one is 0.4, then yes, you get it. Otherwise, you roll it again until you get another one where the difference is greater than 0.1. And then if you get something that's less than 0.4. If you get something that's less than 0.1, then you stop the stream. Okay, so how would you do this? This is not a difficult thing to do. So here's the first approximation for doing this in Python. So here's the definition of a random walk list. It has local variables, so init the candidate elements. So we have some last and some random number 1, some random number generator. And you're going to hold the sequence of these numbers in this list. Okay, this is going to hold to the sequence that you're going to roll, and then you're going to loop, right? So you're going to loop while this rand is greater than 0.1. Then you check if the difference with the last one is greater than 0.4. If it is, then you basically store this current number rand as the last one, and then you append this current number to the list, and you go again. Otherwise, if it's less than 0.4, then I don't know, you print something, and then you basically roll dice again to get another number, and then you test if it's greater than 0.1 and less than 0.4. All right, and so then you go around and you append the last one, and then finally, when you're done, when you got something that was less than 0.1, you stop this iteration and you return the list of these nums. Okay. So, and then from the caller side, from the caller side, you can iterate through the list by, with the for loop or something. You basically have a list of numbers and then you iterate through them and you print them out. Okay, so this is totally trivial, vanilla thing. Now, what is the problem? The problem that one of the problems of this kind of design is that the function is going to generate potentially a very large list of numbers before we print anything out on the screen. Right, so it's stuck here on this loop until it finally sees the end, and only then it returns. So potentially we can call this, and then it's going to be stuck here for a very long time until it generates all the numbers. And only after it generates all the numbers, that could be 10,000, only then it prints something on the screen. This is bad, right? So it's basically we're waiting. There's no reason why we could not print as soon as we have a number. We should print it out. Right, that's what we want. We want a number that obeys these constraints. We should print it out, not wait for the entire sequence of numbers. Also, because it may be in some cases that the sequence never ends. That's an infinite sequence. You have data that's being generated constantly. Maybe you're getting data from the real world, and so there's an infinite stream of data. So you cannot possibly wait for the data to finish before you act on it. Right. So that's one of these problems. So here's a second attempt. All right. So in Python, you can do this. In Python, there's what's called a static function local variable, which is something that remembers. It sticks around for sequence invocations of the function. So you have you have the random number. You check the same thing. Okay. You check if the last of 0. Right, so the last of 0, which is whatever is here, is less than 0.1, then you return. If it's not, then you basically go here just on this little loop just to make sure that you get a number whose difference to the previous one is less than 0.4, okay? This is not going to generate the entire sequence. It's just in case you get a number that this thing is true, then you'd have to generate the number again, right? But now you return. So assuming that you got the number that was greater, whose difference with the previous one is greater than 0.4, then you store it here on this static function local variable, and you return that number immediately, right? So now on the caller side, we make for example, a first call to this function. We get one number. Okay, we don't get the list now. We get single numbers out of this function. And then what we do is, while this is not done, then we print the number and we call the function again, right? So we're always calling the function and then we're getting one number at a time. Now, this is better, but it's kind of clumsy for many reasons, because first of all, the client side is a lot more complicated than the previous one. Right, the previous one was just very clear what is going on. This client side now has all sorts of, we have to call the first one first, and then have this while loop that is sort of calling the function over and over again. So and plus there's this static function, right? There's this static local function. So the API to this function now is a little weird, because now we have to expose the state of the previous execution at the caller side. And so sort of it's a clumsy thing. You can do this in Python, but it's not very pretty. Okay. So iterators to the rescue. So what are iterators? Iterators are exactly the thing that solves this problem. Okay, so first let me show you from the caller side. We're back to the simple, beautiful, API, which is we're on a loop, a for loop. We are conceptually operating on some sort of a collection, right? And we're iterating through the collection. That's what we want, right? This is a good thing. But what's in here now is something slightly different. Now, in Python, we actually have an iterator class, which is so it's an iterator. It's an object. Okay. So what are iterators in Python? And this is true in general. For the APIs are very similar in Java and C# and other languages that support iterators. They are objects that have a very specific API. In particular, they have the constructor, to create the iterator. They have a definition. Okay, I have a question. Why can't we just print the numbers when we append them in nums?
Yeah, that was for the approach one.
Approach one here.
Yeah, first one, yeah.
Right. So because that's not what the spec says. The spec says that we have to have a function that generates the numbers, and then it's the client that decides what to do with the number. We could print it, or you could do something else with the numbers. Right?
Okay,
So,
yeah. You mean like a heavy operation that we can't do there?
Exactly.
Okay,
So
okay,
whatever
okay.
we do with the numbers, in this case, just printing, but it could be something else, right? So it should not be baked in the function itself. So iterators are objects with a specific API that is common in almost all languages that have it, which is they have an iterator function, an iteration method, right? I'm sorry, let me backtrack. So they have the constructor, which you construct the iterator. You have in this case for Python, there's also an iter method that returns the object itself in case you need it. But most importantly, it has a next method. So it has a next method, which is give me the next element of this collection. Okay, that's what it means. Give me the next element of the collection. And whatever it is, whatever the collection is, that's where the logic is going to be. So for example, the next now is just going to be a simple if else with this little while loop in here to remove the ones whose difference is not greater than, whose difference is less than 0.4. Right? And so the next one is a number, a random number that is greater than 0.1 and is whose difference with the previous one is greater than 0 or equal than 0.4 and returns one number. And what's the interesting thing in here to observe? Now we are on object land. Okay, there's an object here, which means that we can hold on to state. Remember, objects are imperative things. We can hold on to state. In particular, all of those other things that we had before that were local variables on the first implementation, and they were sort of this weird kind of static function local variable, now are true instance variables, right? So this is how we hold on to state in objects in general. So now it's an iterator object. We hold on to the state of the iteration. It remembers what, now it can remember what was the last number and what's the current number, right? So those are the two instance variables of this iterator, and we can do things with it. So now the important thing now that Python understands and the other languages that have iterators understand is that when you use a for loop or whatever, this is supposed to be an object that has the method next. That's the important thing, right? So it has the method next, and this is the one that is going to be called, underneath the hood to get to the next, the next thing of the collection. So what's going on in here is that the collection is each number is being generated as it's being needed. Okay, this is not going to generate in everything first and then call the for loop. No, it's only when the for loop asks for the next, that's when this function, this method next is going to be called, and the next number is going to be added to the collection. So it's called a lazy list generation. Okay, it's lazy in the sense that you only run it when you absolutely need it. You don't run it a priori. Okay, laziness is a very important concept, and it shows up in many situations, and especially in big data situations, is absolutely critical that you do things in lazy manner, because you may not have enough memory to hold things, that are pre-computed, pre-generated. So this is basically, you're seeing a first instance of an iterator. An iterator is an object. That's what you need to do. And what kind of state does it hold on to? It holds on to the state of the iteration at any point in time. And how do you get the next object in the collection, the next, item in the collection, there's supposed to be a next method of some sort in these APIs of iterators that gives you the next number according to whatever logic the iterator has to obey. Okay, so it's a little verbose, but the problem is solved here. It's very nice interface over here. So what are iterators? Basically objects that keep the state for traversing an abstract collection, and they are, you can also see them as closures that get passed around in every next. Basically closures and objects are very similar. They hold on, they're little objects that hold on to state. So let me show you the same iterator in Java. So Java has a interface called Iterator. If you look it up, what this interface is supposed to provide is 3 methods of this interface. A hasNext method, which is a something that returns a true or false, whether there are more elements on the collection or not. A next method that gives you the next element of the collection, and the remove, which I don't really know what it, I never really used remove. It's probably remove an object from the collection. I don't know what it does. But the most important are hasNext and next. And so in this particular case, an iteration that does exactly the same thing would be something like that. So hasNext returns true if the current number is greater than or equal than 0.1, and returns false otherwise. Right? That's when it does not have next when the rand is less than 0.1. And the next is the same logic over here. And then you use it like this. This is the part that you are probably familiar with if you use iterators in Java or C# or whatever. So in this case, you instantiate one object of that class, and then you go in a loop like while it has next, then you call the next, right? So I'm sure that's those of you who've done Java, you probably have done stuff like this, okay? But you've done it on collections that are coming from the JDK, so you've probably never done your own iterators. But there's nothing really magical. This is what iterators are. You just need to provide these 2 methods, hasNext and next, and then whatever logic of that particular iterator applies. Okay, so these are iterators. Bottom line, what are iterators? They are objects, plain vanilla regular objects with these interfaces that very specific, that in particular the next method is very important, and it's present in all of the languages that have iterators. And the state is supposed to be the state of the iteration at any point in time. Very simple. So this is great. You have iterators in Python, in Java, C#, and lots of other languages. But let's go to the next level, because iterators, as you can see, they are nice in conceptually, but they add a lot of verbosity. So there's a lot of verbosity, and there's this API that you kind of have to know about. So another way of doing this in Python and in certain other languages is with generators. Okay, generators solve the same problem that iterators solve. Okay, the problem that they're trying to do is exactly the same problem, which is to how do you avoid having to generate the collection up front, right? How do you avoid that? And conversely, how are you able to have a collection, a lazy collection, something that is generated as you need it, right? So that's the same problem. Iterators do it with an object, just like I explained. Generators are slightly different. So in Python, generators are functions that yield values every time that they are called. Okay, so here's an example of a function. This is the part where having a Python interpreter might help. Let me see if I can do a Python interpreter here. All right, so this is an iterator. I'll come back to this one, but I wanted to have I'll come back to this one. let me go back here and I have a Python thing here. What is this? Okay, I have it here. Great. All right, so here's an example of a function. I call it crazy. And the body of the function is this: yield1, yield2, yield3. Okay, so let me put this. And for those of you who have never done yields, let me show you what this does. Okay, so now I have this function crazy. So if I call crazy once, sorry. No. Sorry. No. Oh, I know. I always forget. They changed this at some point. So, okay. So, for example, C equals crazy. This is how you call iterators in Python. So you say not C. So this is going to be the generator. But you say C. Damn it! How do you do this? I always forget. I should have had it here. Does anybody remember how to call the generators in Python?
I think you have to do a next crazy.
Next. That's right.
I'm not sure. Python isn't my primary language.
Yeah.
Next and then call crazy in the as an argument to next. Maybe.
Like this?
I think I'm not sure. You can.
Yes,
Yeah.
that's right. Okay, good. So if I call crazy with this next function, I get 1. And then if I call it again, no. Oh, no. I remember what it is. Okay, so it's next C. That's right. That's how it goes. All right. So let me backtrack. So if I say, let's say A equals crazy, okay? So I have this A that is a generator, all right? And so the way that you work with generators in Python is by using the next function, okay? And now if I say next A, you're calling the next version of the next execution of the generator A. I get yield a 1, and then if you call it again, I get yield a 2, and if you call it again, I get yield a 3, and if you call it again, I get an exception stop iteration. Basically, there's no more, and there's no more because there's no more. So let me tell you what is going on in a function that has yields. So a function that has yields, when you call the function, you run whatever code is there until you hit yield something. Okay, so when you hit yield something, there's sort of a local return from that function to the environment that is being that is calling that generator, right? So then you got the 1. But if you call it again, when you call it again, you don't go back to the beginning of the function. You go back to the place where you left. So the place where you left in this particular case is this line 3. So you go back to here, and in here there's another yield. So this returns a 2, and then when you call it again, you go back here to the yield 3, and then you get the 3. And if you call it again, you reach the end of the function. There's nothing else to return. That's why you get this exception here. Okay, so the yield is basically a yield is a return without popping the stack. If you want to put it this way, it's not exactly this, okay? But if you want to see it this way, it's a return that doesn't pop the stack. Or in other words, it's a return of a function that does not go away. That the context of execution of that function stays there, so that when you call it again, it goes back to where it was executing. So here's a more interesting function over here. So this is a function that's supposed to return the first n up to, the first numbers up to n, I think. So you start with the 0 and until the this local number is less than the maximum. Then you yield that number, right? You return, and then if you call it again, then you come back to line 10, which means that it's only now that you're incrementing it and you go back here and then you yield the next one. So let me show you what happens if you say first n. Okay, now if I say, f equals first n of 10, for example. All right, so now if I say next f, I get 0, now I get 1, now I get 2, etc. Okay, till we get the end, which means that we already, this thing has failed and we are at the end of the function. So there's nothing else to do. So the important thing here, that the interesting thing about the yield keyword for in generators, so these are called generators. So these are functions that have this yield method. It's that the function, unlike the other normal functions that return and then basically go away, when you have a generator, the context of execution of that function doesn't pop. It stays there, and it remembers where it was. Okay, so when you call it again, it goes to where it left, not to the beginning of the function. Okay, this is really important to understand. When you call first n again, it doesn't go here. It goes to here, line 10, which is where you left. All right. So these are what's called generators. So basically, we have the ability to keep generating things, right? Just yielding things without the function ever popping. The function continues there, and it's a lazy thing in which we can call it to get the next one. So it's doing the same thing as the iterators. We could do this with iterators, but it's much shorter and concise, right? The problem here in terms of expression is that may be a little bit more confusing for people who are not who don't know, right? So now you need to know about this concept of a yield and what it does, meaning that the function doesn't go away. So now you need to know about that. But once you know about that, then expressing things with generators is much nicer than expressing things with iterators, like 10 times nicer. So if you go back here, here's the same problem done with the Python generator. Okay, this is so much easier, so much smaller, right? So much simpler. So here's a random generator, the same generator. If the conditions are all true, then you yield that number, right? So you yield it. That means that you have a local return to the caller. But if you call the function again, then you come back here, right? And then you basically are inside this loop that you haven't stopped yet, right? This loop is still active, and the context of the execution is remembered, right? And so, and from the client point of view, it's the same interface as if it was an iterator, but from the implementer's point of view, it's much simpler. I mean, much simpler. So yield is a powerful concept, generator. So C# also has generators, so that you know. So here's the same generator in C#. And in C#, it's not just yield. You have to use yield return. This combination of keywords, yield return in C#. But the concept is exactly the same. It means that you have a local return here, but if you call it again, you come back here. You don't go back to the beginning of the method. You go back to where you left. So basically what it means, the function doesn't go away. It remembers where it was. And this is how you call it. So the you may want to read more about the magic yield and how it relates to continuations. But basically what is going on in here is that when you have a a generator function, and this concept of a generator function, it really means that, what we learn and what I taught you about the way that functions are implemented, which is where every time that you call a function, there's a new frame that gets added to the stack. Then when you return, that function is popped out the stack. All of that does not apply here. That's what I'm saying. So generators are these special functions. In fact, these are objects in a way. Okay, they're basically very similar. In the implementation of generators is almost identical to iterators, except that it's done by the compiler rather than by us. Okay, but basically it's a little piece of data, okay, that sits somewhere and remembers what was the last state of the iteration. Right, and that frame, that's freestanding frame, doesn't go into the into the stack. It just stays there in the heap until the collection has been exhausted, until the collection, there's nothing else to generate, right? So that's an interesting, really, really interesting and powerful concept, and kind of opens up your mind of the way that we think about functions in general. Because now, so far, everything that I talked to you about functions is that there's this model of, you call a function, and as you call another function, and there's this stack of functions, the stack that you can trace to see, where you came from to where you are, and then when you return, you pop. But in fact, this is just one possible implementation. And to tell you the truth, it wasn't even the first, because we had functions in the 1950s already. The functions were already a thing, even before we had the concept of stacks and stacking the invocations of functions. So, and once you realize that actually the stack model of managing functions is just one option, then there's a lot, suddenly there's a lot of interesting things that you can do, right? So if now we can actually hold on to functions and their state of execution, there's lots of interesting things that we can do that we probably never even thought about. So I'll talk more about the new avenues that open up. But basically, generators, there's no generators in Java. So if you want to solve this problem of infinite collections, then you have to use iterators of some sort. Okay, some sort of iterator concept is the thing that you kind of need to have. In C++, there's also no equivalent. But I heard, I kind of lost track from C++, but I think there are some notion of coroutines in C++ that I am not entirely familiar with, but I'm going to talk about coroutines next. But all the other major languages have support for generators, because they are definitely very, very, very useful for, collections. And we're talking about collections, we're talking about data. So now that I talked about this idea that you can have these generators that are functions that stick around, then let's really open this can of worms, okay? This idea that you can actually have functions that stick around and you don't have to stack them. You can have many functions executing at the same time. And we already had that, and that's why this is related to concurrency in a way, because when you have concurrency and you have threads, you also have many functions at the same time, in the sense that you have many stacks, right? So you have many different, each thread is its own stack. So as each thread goes through a sequence of method calls or function calls, that each stack is independently managed, right? But what I'm talking about here is not threads. I'm not talking about threads. Forget about threads. Let's imagine that you have just one thread of execution, but that you actually have functions sticking around. Okay, and what kinds of things can we do? That's basically coroutines. Okay, coroutines mean routines that coexist, things that are active at the same time. And let me give you an example. So basically, there are procedures that not only generators are very constrained examples of coroutines. Okay, so that's why I kind of coroutines is kind of the more general version. Generators are coroutines, but they are very, very constrained, because when you come back to the function, you come back exactly to the place where you left. So if you open that can of worms, you can imagine coroutines where when you come back, you can come back to any arbitrary point of the function. which is a little crazy, but this is in the beginning when we started doing computer things. This was a perfectly valid thing to do, and a perfectly question to ask. Like, you have two functions in memory. You switch between executing little bits of this one, and then you execute little bits of that one. But maybe you want at some point when you go back to the second one, you go to some other point for whatever reason. So there's all sorts of crazy ideas out there. So there are procedures that remember the last set of their execution. They call on each other as peers rather than caller and callee. So here's some appropriate scenarios. I'll give you an example. I'll give you more examples of languages that have coroutines very successfully. But here's a scenario: a function that produces a stream of data and a function that consumes a stream of data. The question is, which one calls which? Do you pull or do you push? Right. So here's an example of a situation where you have suppose, for example, that you get a character that is compressed in some way, and you decompress the representation, and then you parse and get what kind of character that is, for example, or you get many characters and then you emit a word of some sort. So in this case, so this is the kind of the logic that we want. There's a part of the code that decompresses the character, and there's another part of the code that checks if it's an alphanumeric. So it gets many characters, check if it's an alphanumeric, and then when it gets a non-alphanumeric or whatever, it emits a token punctuation and then a token word. But the question is, which one is the dominant one? Okay, I'm sure that many of you have had these doubts sometimes in certain situations. So one way that you can do it is that the parser code is the dominant one. So the parser code, as it needs characters, it calls the decompressor, right? So it calls, here's the decompressor is a passive function, and it's this parser code that is the active one that kind of asks characters from the decompressor, right? So this is kind of a pull mode, pulls characters. But you can do it the other way around, right? So you can also have the decompression code that is the active one, and the parser being the passive one. And so every time that you get a character and you have enough words, then you say parse this character, right? And then it's up to, and then at this point it's up to the parser to emit the tokens. So you can do it the other way around. This is a push model. So you have the pull model and you have the push model, and those are all valid, right? But what they have in common is that one of the functions dominates the other. Okay, they are not peers. One of them is dominating the other. One of them is calling the other. So doing this, you can also do this with coroutines, and I'm not going to go through the details. I'm not even sure that I understand. This is some sort of a dialect of C that I found on the internet. It's an example of how could you do, just to explain what having peer functions do. But basically the idea is that you have two functions, all right, and none of them so basically none of them calls the other as such. They just switch between each other. So at some point you get some sort of a return, basically a local return from the function. Is basically a yield, some sort of an yield that takes you to the other function, and then the other function does whatever it needs to do, and then it yields at some point so that it comes back to the first one, and etc. So that's basically a coexistence of these functions, and when they come back and from one place and another, they just keep bouncing from whatever execution they were, where in this code they were. So from here to here it comes back to here, and then here it goes back to where it came from, and this one executes a little bit more. It comes back to where it came from here. So there's basically a coexistence. So this is the conceptual model of coroutines. So they are not just pairs of functions, but it could be any number of functions. I just show you two, but it could be more than two. Okay, it could be a collection of functions that they are all coroutining together. Functions can specify which other functions to yield to. I didn't show you that, but that's valid. That's also valid. So basically, how to implement this? You can have a sort of like threads. Basically, you can have a stack per coroutine, or you can do it with continuations if the language supports continuations, which is basically these higher order functions. And it's basically a lightweight alternative to threads. It's no real concurrency. It's just switching functions. And definitely not. Let me backtrack. It could be real concurrency if the language implementation decides to actually apply real concurrency. But the model here is that there are no threads, okay, as such. There are no threads as such. There's these lightweight functions that stick around, right? And that the execution kind of switches between ones and the others. Now, so it's a lightweight alternative to threads. It was a very nice model of concurrent processing for data, especially for data streams. But it kind of fell out of favor in the 80s, and the reason was clear. It's because it can give rise to very confusing code, right? It's basically glorified go-tos. It's sort of a structured programming version of go-tos. And so it can be very confusing to kind of track where, for us humans who program these things and read these programs, it can be very confusing to track where you are. But it is seeing a comeback. It definitely saw a comeback, and one very it's not very popular, but it's a really interesting language. I don't know how many of you know about it, but Lua. Does anybody know about Lua? Okay, so there was another, I'm sorry, there was another question from Aditya about how does yield work with threads. Before I talk about Lua, let me address this question because this is an interesting question. Threads also have in their APIs, there's typically also an yield method, okay? Don't confuse the yield method of threads with the yield keywords of generators. Okay, they are again very similar, but they're not the same. So when your thread says yield, it denotes to the scheduler, the thread scheduler, say I can yield my turn. Let's just put me on the back of the queue and run some other thread. That's what the yield in threads mean. Okay. That's what it's just a directive to the scheduler saying, hey, I can be put on the back of the queue. Just run some other thread. The yield keyword in generators means something specific. It's a local return. It returns something, right? It returns something to the caller. Okay, so as usual in programming world, there's so many instances of this that we use the same word to denote concepts that are fundamentally different, that they are related, but they are fundamentally different, and things get very, very confusing. So don't confuse the yield of generators with the yield that you find in the APIs of threads. But to be very concrete, respect to your question, how does yield work with threads? Yes. So when you have a multi-threaded programming, for example, in Python, right? And then there's an yield there. Then it yields it within that particular thread. It's just that particular thread, not the others. It doesn't affect the others. So it just does it's that thread that reaches a generator, and that generator does a local return to the caller of that generator, and that's all happening within the same thread. So it doesn't the yield of generators has absolutely nothing to do with the threads of Python. Okay, is that clear, Aditya?
Yeah, that's fine.
Yeah. Okay, so let me talk about Lua. Lua is an interesting language. I know how many of you have heard about Lua or used it? Does anybody know about Lua? Okay, Lua is a really interesting scripting language that is used by some game engines. Particularly, I think the Unreal Engine is very popular for people who do games. And let me tell you, it's an interesting situation. It's a really, first of all, game engines are super interesting. Okay, software, as a software systems, they are really, really interesting pieces of software because there's like the whole operating system right there. Game engines are amazing beasts. But so they have everything, and yeah, exactly. I mean, it's really amazing what game engines do. They basically take over your computer, and they almost replace the entire operating system when they run. But let me tell you why. Because they are doing a lot of stuff. They're basically really literally taking over your computer. They take over your screen. They take over your peripherals. They basically, to run the game as fast as they can, they take over everything. Now, what games usually are, from a point of view of developing these games, okay? So people, you have the artists that do the art, the monsters and whatnot, but then you have to animate these objects, right? You have some bot that is saying something to the player, or you have some object, an orb or something that is rotating and irradiating something, or that is active, that when you click it, it does something, right? So these objects in the game have behavior, right? They are programmable. And they are programmable by the developers of the game. Sometimes in some games, they're actually programmable by the end user. So there's some games that we can actually add scripts to the objects. So there's a need, in other words, there's the need to script the game objects. Minecraft, for example. Minecraft is a wonderful example where it's the end user that programs these objects, right? And so Minecraft opened up this scripting all the way to the end users. But other games like World of Warcraft or whatever, the scripting is not quite up to the end user, but it's the game developers. There's a layer of the game developers whose job is to script those objects, right? And so the question is, how are you going, if you have a game world that has, for example, 10 different active objects that are interactive objects that are doing stuff, and that can react when you click them or something when you interact with them. The question is, what's the right model for running those scripts, right? What's the right model for, first of all, for specifying those scripts, and for executing them? Because clearly, those objects, so it's really different people who program those scripts versus the people who actually program the C++ or whatever that of the game engine itself. It's two different kinds of people. So there's a layer here of scripting that is much more accessible and much more easily available to people who are not necessarily super experts on low-level programming. And so these scripts are typically associated with the game objects. They're written in some some language, some scripting language. We have in real language in the Unreal Engine is Lua. In Unity, you can have scripts in like JavaScript or C#, and other game engines you have other, either some special purpose scripting language, or JavaScript is also now very popular because the JavaScript engines are open source and readily available. But you have a scripting engine embedded in the game engine. So the game engine is this gigantic monster, as I said, and including always some sort of a part of a game engine that is the script engine that runs the scripts of these interactive objects, right? And so that scripting engine needs to be able to run these 10 interactive objects concurrently, or at least with the illusion that they are concurrent, because whatever this object on the left is doing is supposed to be at the same time as this object on the right is also doing. So you have somehow to multitask, right? You have to have the illusion of concurrency among all these different objects. Now you could say, okay, let's give every game object that has a behavior, let's give it a thread. Okay, that would be a possibility. That is usually a bad idea, and that's not something that the professional game engines do, because literally in these in game worlds there can be thousands of interactive objects, and now suddenly if you give a thread to each of them, things would just crawl to a halt, right? To be super inefficient if you had like thousands of threads with all this context switching that is going on between the threads, that would be really bad performance. So that's not what the game engines do. So what do they do? For example, the Unreal Engine and others, the Unity engine too, they either have a constrained version of threads, or they go all the way to coroutines. Basically, what these scripts are going to be coroutines, right? So you have functions. They are are going to be functions that are going to stick around, basically, and you have one thread or more, or but a limited number of threads that execute these coroutines, and that basically switch the execution. They execute a little bit of this function of this script over here, then they switch to that other script, they switch to that other script, that come back to this other script. Basically, they do a very lightweight version of threads that are not threads, they are coroutines, the functions that stick around. And so Lua is a very good example of a scripting language that took this old idea of coroutines that had kind of fell in disuse, and made it a success in the Unreal Engine. So coroutines are definitely coming back. So let me see. I have an example. I wanted to talk about something else also. So that's the right. So that's the idea of coroutines. So you don't have coroutines as such in not many languages have them. Maybe Go has it. Does anybody here know about Go? Is it Go that has coroutines? One of these modern ones.
Go has channels and functions which are kind of like coroutines.
Okay.
So
All right.
yeah, they're like lightweight threads, I guess.
Lightweight threads. Okay, yeah. So they're probably more coroutines than threads. What was the other one that I forget? So as I said, they fell in disuse, but they are coming back because they are definitely interesting for as an alternative to very heavyweight threads. Okay, so what do I want to talk about next? I want to talk about one last thing here on my REPL, not this one, but the other one. This one. All right, so I have two versions of I don't know if this is the same program or not. It may be. Okay, it looks like it's the same program. So here's a program that I have that I honestly I don't remember the logic, but it's something like this. You have a sequence of iterators. So you have actually 3 iterators, if I remember correctly. That's right, 3 iterators. And what they're all going to do together is that, so the first one generates a random integer between 0 and 100. The second one gets gets one of those, and it checks if the last one if it gets the number 50, it stops. Okay, this is the stopping condition. Otherwise, it checks if it's even. Right, if it checks if it's so it ensures that it's even, and then the third one remembers the numbers, the prior 2 numbers, actually gets 2 numbers from the stream, and returns the sum. So if I remember correctly, this generates a stream of numbers that are the sum of two numbers that are integers, or even. Let me see what this does. Might as well just run it. 28. Oh, crap. Okay. Java C main.java. All right, so I have to remember what the logic is. So the number is 20, and then it got 50. Right, if it's 50, it doesn't pass it through. When does it stop? That's what I want to know. Oh, it's continuing. Okay, I wrote this a year ago. I don't remember the logic anymore, but it doesn't matter what the logic is. It really doesn't matter. You can try to read it. I can make this available, but it doesn't matter. What matters is what is going on in here. What's going on in here is that you have 3 iterators in a sequence, okay? And what is going on in here is that so you have to see this as a sequence of 3 little functions, okay? And at the bottom, you have what's called the sink. So the thing that pulls the data, so which is the main method, okay? So the main method is the function that pulls the data from the stream. And this is what I'm using the word stream, not necessarily to refer to the streaming APIs, but literally this is a stream of data, okay? And so it's from a source to a sink. And in this case, the sink is the main method. And so the main method is the one that on this loop, it checks whether the last one, the raw 3, still has elements in the collection. And if you check what that means, in this case, it is true if the previous one is true. And if you go back here, if it has next, it checks if the last one, it pulls one from the previous one. And then if it's 50, this is the logic that I don't remember anymore. You can try to remember, but it's some logic that stops the stream at some point. But so if it has next, then it prints out that number. Okay, so this is the one that is pulling the data from the stream. All right, and so each of them is doing its own logic, whatever it is. I just put some random things when I did this. I don't even remember. It's something very silly that now I cannot remember just by looking at it. But this is similar to the exercise that you're going to do this week. If you do it in Java, okay, if you do it in Java with the iterators, then what you want to have, the model that you want to have in your mind is that you're going to have a sequence of iterators. And the source that is pulling the data from all this sequence is the main method that is consuming that data. And as it consumes the data, then the source generates more data, right? So that's the idea that is going on in here. That's the lazy reverse method. So perhaps I should just go here and talk about the lazy reverse exercise that you're doing this week. So what is going on in here? In Python, I'm using generators because generators are much nicer than iterators. So here's what's going on. So I read the file name. I read the file, and I read one line at a time. Okay, now you know that what's going on in Python. When you do something like this for line in open file name, it's also a generator, by the way. So it's a lazy thing, and it yields one line at a time, as you know. But I am going all the way to actually split the line in characters, right? And I'm yielding a character at a time. Okay, so I have another inner loop over here that is yielding characters. Okay, and then I have another generator over here that iterates through the characters. Okay, the characters being a generator, so it's a lazy iteration, right? It doesn't have all the data a priori. It just goes as it needs, and does the parsing of the characters and until it finds a word and yields words, right? So it takes characters and yields words. And then you have the non-stop words generator that takes words and yields non-stop words. And then you have the count and sort generator that takes basically the non-stop words, iterates through the non-stop words, and it yields. This is an important part, okay? Because this is, and these kinds of styles are good for these streams of data, and the streams of data might not even end, right? It could be an infinite stream of data. I could be reading from a network that would be constantly sending characters or lines or whatever, right? So, but at some point I want to print something. So the way that I'm doing this is that I'm buffering, or I'm sort of windowing. It's perhaps a better word. I'm windowing the data, and in this case, I'm windowing the data at 5,000 non-stop words. Okay, so here's what I'm doing. I get, I'm counting the number of non-stop words with this I. Okay. Why am I initializing the I to this thing? This is a bug. Okay, I should be 0. Anyway, when I've seen 5,000 non-stop words, then I yield a sorted dictionary. Okay, I yield a sorted dictionary and I print it. So basically, this program, if you run this program, it's not going to be like the others where you only print one thing at the end. It's going to print every 5,000 words. It's going to print an updated count. Okay, this is what's going on in here. All right, and this is a typical use of streams, that especially when, again, very long running streams or infinite streams, that you still want to kind of check what is going on at some point. So you can window at some point and see, it's called, in the streaming APIs, it's called lacking the words, not reduce. It's another word that they use. Collect the data, right? So at some point you finally can collect the data, right? And that kind of makes makes the laziness, actually, that's when you actually make the whole thing work and end up with the evaluation of the thing. Okay, so this is what is going on in here. So what is going on in here is that the way that the model that you have to have in mind is that there is a source of data, in this case is the file, okay? There's a sink of data, which is the one that is going to display things somewhere, all right? And in this case, it's the sink that is pulling the data. So this is a pull model. So it's pulling the data from upstream, right? It could be the other way around. Sometimes you can also have the other way around, which is the source of the data that is pushing data down the stream. But it typically, in the lazy modes and the streaming API, is actually this way. It's the sink of the data is the one that pulls the data. And so basically you have to, the way that you see this is you have these generators, which are all functions that are all active at the same time, right? They're all active at the same time. You don't have one that calls another and then goes away. No, and you don't have any point in time here large amounts of lists or whatever, collections of things that stick around. No, it's all on demand. It's only when you need it that you go and get it. You don't have the entire thing like in the other implementations that we did. Okay, so this is a very efficient way, memory-wise, of processing big data, right? That you don't need to have all the data in memory. You have, but especially when you have these pipelines. This is what Sarah was talking about on Tuesday. When you have these pipelines, you really want the pipelines to be working as fast as possible on the data. You don't want the some function here to have to wait for all the data in order to start working. No, you want the data to flow through these pipelines. And so that's exactly this kind of streaming that is going on. This is what's going on in these streaming APIs, okay? Where you have the data streaming. So if you use a language that has generators, then this is a typical good use of generators, right? If you want to do this in Java, then you don't have generators, but you can do the same thing with iterators. And so that's perhaps what I was talking about here. So if you want to do the lazy rivers in Java, you can do it in two ways. You can either do it with just, as I said here, code your own generators. So basically what's going to happen is that each of these functions, each of these generators that I have here is going to be an iterator in Java, right? And it's going to do basically the same thing, except in the iterator style. That's one way of doing it. Or another way of doing it, if you want to take a look at the modern streaming APIs, you can also look into the streaming APIs of Java that basically are the lazy river style. And what they do, they provide you with an API, high-level API that essentially does some version of the iterators underneath, basically. And so you can use this exercise to learn about the streaming APIs. Now, I don't know why this is squiggling, or why I had maybe I never heard. Is I don't know. Maybe it doesn't return. Maybe this is still going on. Okay, something like that. So so to come back to the point that I wanted to make, that so streaming APIs and the concept of streaming is a very important one these days. It has to do with applications that process data. It's particularly large data or long-lived data, right? And this idea that now you have sequences of functions or whatever, iterators or objects, sequences of objects or functions, that each of them is doing something on the data, processing the data and transforming it and passing it to the next one. You have these pipelines of processing. And the important thing is that the important thing that why this is different from just the regular vanilla pipeline, that style that we studied up in the beginning of this course, is that in that, let me go back to make sure that we really understand the difference. If you if you go back to the pipeline style over here, so the pipeline style, if you just do just a functional pipeline, what is going on in here is that there are indeed these large intermediate lists that are being generated. So for example, the read file function reads the entire file, right? And puts all that big string, passes to the next one. And the next function returns a list of pre-computed words or whatever it is, another string that has something normalized. So there are these intermediated, very large lists that are being generated. And each function computes the entire output before giving it to the next function. Okay? So this is sort of the vanilla functional pipeline. What is going on now in these other styles of the streaming style is that it's still the same pipeline, essentially. Maybe, I don't know, maybe not, but it's still a pipeline. But now all the nodes of that pipeline are active at the same time. The data flows through them. You don't have at any point these large intermediary collections of data. Okay, there should be absolutely the minimum amount of data every time in this flow for all the functions to actually be working. That's the idea. This is the concept of streaming. Now, why is this related to concurrency? So it's typically related to concurrency because now you can see already, because now we have all these activations, like these functions are all active, right? So you could imagine that in certain circumstances, depending on what the pipeline is doing, you can actually make certain of these things in parallel. You have things that are working in parallel. So in particular, if you're executing, a sort of map reducible problems or map reducible data, some of these nodes could be executing in multi-threading kind of style. Okay, so there's opportunities to do those kinds of optimizations under the hood if you have this kind of data flow kind of programming. But it's not necessary. Okay, so the concept of a stream, the model of a stream is not necessarily the same as concurrency. It doesn't necessarily need to have concurrency. You still, for example, in this particular example that I'm showing you here, there is no concurrency. Okay, there's just one thread in here in Python. But nevertheless, it's this idea that you minimize the amount of data that is going on through this set of active functions that are all active at the same time, that don't go away, right? So yes, so streaming APIs are super popular these days because big data, and I would encourage you to take a look at the streaming APIs for doing this particular homework, especially if you're doing it in Java. Otherwise, also take this opportunity to learn about generators in whatever language you are using, or iterators. Iterators are also cool things. Generators are much nicer. They make things a little shorter, but if your language doesn't have generators, just stick with iterators that they do the same thing.